remember that the difference between the average of a product and the product of the averages is a covariance. And if I normalize that covariance by dividing through by average income and average welfare weight, I'm going to call the negative of that sigma. Now, why negative? Well, the poor are going to have a higher welfare weight than the rich are. And so the covariance between income and welfare weight is going to be negative, right? So this is always going to be a negative number. So I'm going to make sigma be the negative of that. OK. So we're going to, this formula becomes, if you just work through it a little bit, that 1 minus tax times the elasticity over 1 minus tax is equal to sigma. Or the optimal tax is equal to sigma over the average elasticity of labor supply plus sigma. Now notice that the tax increases when we increase sigma, and it declines when we increase the elasticity. And that captures the trade-off between equity and efficiency. Can anyone explain why that's the case? Yeah, Carl.
Because when elasticity is high, there's a big efficiency cost of taxation.
Yep.
And when sigma's high, there's big equity gain.
Well, in particular, what does sigma sort of measure? What thing that we've been talking about does it measure?
The covariance.
Yep.
Between average income.
And what's going to lead that covariance to be big? Exactly. Yeah. The more inequality that there is, right, the more variance there's going to be in income. And given that income and 1 over income are moving in the opposite directions, it's sort of just a measure. It's like a logarithmic measure of how much variance there is in income, right? OK. So the yeah, this is just what we said. So this provides a very simple formalization of the equity efficiency trade-off. If inequality is very large, unless we have a very high tax, because there's so much inequality that even as we tax a lot, we're still having a lot of inequality, then the tax rate is going to be very close to 1. On the other hand, if the elasticity gets small, we're also going to have a tax rate close to 1, and opposite in the opposite directions, right? So the more inequality there is, and the less elastic people are, the higher we want taxes to be. OK. So that's a model that's supposed to cover what's going on for sort of most typical Americans, right? But you know, Obama has recently been pushing for having an extra tax on the super rich. And the thing to notice is that when taxing the rich, their welfare hardly matters at all. Why is that? Well, 1 over $1 million is about 1/20th of 1 over the average income, $46,000. And so basically, the amount that it hurts the rich when we take $1 away from them essentially doesn't matter at all. All that matters is how much revenue we can extract from them, right? So we can simplify the problem in this case by just thinking, let's extract as much money as we can from the rich. OK, so suppose that we raise the marginal tax rate that we're charging on anyone who's earning over $1 million, right? Let's let the average income of people who earn more than $1 million be I bar sub 10 to the 6th. What are going to be the two effects that are going to occur on our revenues when we raise tax rates on those people? Anyone? Yeah, Chrissy.
One of them is that they'll be discouraged to work.
Yeah. And what's the other one? Very simple, even simpler than that one.
Was it the one that was called mechanical?
Yeah.
I forgot what it is.
It's just the tax is higher, so we get some revenue out of them.
Okay.
Right? So that's like the simplest possible one, right? And in particular, we get this tax rate on the income that they earn above $1 million. We don't get it on the income they earn below $1 million, right? So when we, so their income is going to fall by their income multiplied by the average elasticity of income at that level divided by 1 minus the tax. And so that reduces taxes by tax rate times that, right? So the total effect on our revenue from people earning income I is that income times 1 minus this formula that we had before, minus 10 to the 6th, because we only earn the income when we raise it on their money above 10 to the 6th, right? So the optimal tax rate equates this to 0. So if we now take averages over everyone who's earning over $1 million, as we did before, we get I bar 10 to the 6th times 1 minus this, minus 10 to the 6th, and we've got to set that equal to 0. Now, when we've taken the averages, the elasticity now becomes the average elasticity of income for people above 10 to the 6th dollar, again, weighted by income, right? OK. Now, I want to define alpha to be the average income of someone earning above $1 million divided by the average amount that such a person earns above $1 million. So the average income minus $1 million. Now, if we use the same logic that we did before to solve for optimal tax rates, what formula are we going to get now by equating this to 0? Neil, can you derive that on the board? Or
by equating what to 0?
This first order condition up here, setting this equal to 0. Can you solve for what the optimal tax rate would be?
So that is the first order condition? Or
Yeah, that is the first order condition, right? Because we took the derivative of our revenues with respect to the tax rate, right? And we got that they're equal to that, and we want to just maximize the tax revenues that we get.
Sure. So we can take 10 to the 6th over
To the other.
over 10 to the 6th.
Yeah.
Minus 1 minus that.
Yeah. That's good. And what does that give us? Make a common denominator between 1 and that?
Right.
Yeah. You can do it on the board if you want. It's actually up there. You can just walk us through what's up there.
Okay, great. Yeah.
Yeah.
Okay. So, yeah, we took 10 to the 6th the other side divided.
Yeah.
Where do we actually get isolate t?
Not yet. So then we get 1 minus this, right? Now make a common denominator. What do we get?
We get I out of the 10 over I to the 10, so 1 over alpha.
Yep, exactly. And then you set that equal to this.
Sure.
Now you can try to isolate t by multiplying, right?
Multiplying that, okay, yeah. And that's t, so those aren't a's, those are t's.
Yeah.
All right. And then we can take all the a's to one side there, yeah. So you get 1 over alpha times t times 1 over alpha plus.
Yep. Epsilon bar.
Epsilon bar, yeah.
And then divide through by that, right? OK, that's good. So we actually, in some sense, get exactly the same formula as before, except that 1 over alpha has replaced sigma, right? And epsilon bar for people earning over $1 million has replaced the average elasticity of income for people in the general population, right? So the nice thing is that we're going to see that alpha actually measures inequality in the upper part of the income distribution as well. Why is that? Well, this is sort of a measure of how much, if people are earning a lot above $1 million, divided by the average income that people are earning above $1 million, that means that the people are earning like way more, right, on average than they are. So there's like a lot of stretching out at the top of the distribution, right? Imagine that this were equal to 1, right? That would say that all the earnings of a typical person earning above $1 million are above $1 million, right? They're not like, on the other hand, this would be 0 if everyone earning above $1 million was earning like $1,001,001, right? So that sort of shows how much at the very top of the income distribution things are stretched out. And we'll actually relate it to the properties of Pareto distribution in just a minute. So again, the equity efficiency trade-off is going to emerge. In particular, under what circumstances should taxes be progressive, does this indicate? Anyone want to say, what case should this be greater than the formula we found before? Yeah, Mohammed.
So like here we have elasticity of rich rather than like elasticity of equity. So
Yeah.
if like rich are less elastic to taxes,
Yeah.
that would help us. Like, so we can raise taxes.
Yeah.
And instead of the sigma, we have 1 over alpha.
Yeah.
So if that 1 over alpha is like that they is like the reverse of inequality here.
Yeah.
The equality is like larger than our equality that was like sigma.
Yeah.
Then we can also.
Yeah, so what that basically says is that if the inequality among the wealthy is greater than the inequality among the general population, then we're going to want to have progressive taxes. On the other hand, if the rich are, on average, less elastic than the rest of the population is, we're going to want to have higher taxes on the rich. Now, I just showed you before that while the Gini coefficient has been rising a little bit in the United States, so the inequality among most people has been rising a little bit, mostly it's been that the super rich have been getting much, much richer. So that indicates that taxes should be getting more progressive in the United States. On the other hand, in Europe, the top income shares have been coming down while the Gini coefficient has been relatively stable, indicating that in Europe, taxes should be getting less progressive, holding fixed the elasticities. OK. So in fact, what we're going to find is that there's a very tight relationship between the Gini coefficient and sigma, and a very tight relationship between the inequality at the very top of the income distribution and alpha, which is very intuitive and maps what we were talking about at the beginning of the lecture right into what the redistribution that we want to do is. OK, so to do this, let's use a log logistic distribution for income. That's very similar to log normal that you've been using in a lot of your problem sets. I think you might even have used a log logistic at some point, and it makes a very nice, very, very easy to solve. So it turns out under log logistic distribution, beta is exactly 1 over the Gini coefficient, which is kind of amazing, and is going to mean that sigma is very closely related to the Gini coefficient. And you can then equate the mean of the distribution to, so for in the US, it's 0.45, so beta should be 1 over 0.45, and the mean should be set equal to the mean of the log logistic distribution, which gives alpha around 32,168. So if you throw this into Mathematica, you get that as a function of the taxes, the sigma is like this. Now, why does sigma decline as taxes increase? Because you're reducing the inequality in the distribution as you raise taxes. OK, so we can then just graph the right-hand side of this equation and then put t on the left-hand side and solve for the optimal tax rate. And here's what you get. So if the elasticity of income is about 1, total taxes should be about 26% or something like that. If elasticity is 0.1, they should be about 65%. Now, where are we in the United States? Well, if you add up local, state, and federal government, they're sort of on average taking about 30% out of the economy. So we're somewhere around here, which would maybe correspond to an elasticity of about 0.7, 0.8. OK. Now, calculating alpha is actually even easier, because remember that the upper part of the income distribution is Pareto distributed with a coefficient of alpha about 1.5 in the US and about 3 in Europe. And that is very closely related to the upper income shares. So alpha has been